This is lesson 11 of the No Frills A-Level Physics lesson series, Whiteboard Physics. Lesson 11 is about the photoelectric effect, which is the first introduction to quantum phenomena. So we need to tell you a little bit of a story, not a complete story. There'll be more to follow in future lessons. But a little bit of a story. A chap called Heinrich Hertz was doing experiments. He was doing experiments with newly discovered waves that were emitted from sparks. These were radio waves produced when there was a spark, and he was measuring the speed of these radio waves. And we look more at that experiment much later in the course. Anyway, while he was doing this experiment, he discovered, and we don't know the details of how, that when ultraviolet light, ultraviolet radiation, was shining on the gap, on that spark gap, he got stronger sparks. This was interesting. Why do we get bigger sparks, stronger sparks, when there was ultraviolet radiation? And it was a bit of a mystery. He didn't understand why this happened. So, observations. What did Heinrich Hertz observe? Well, it wasn't necessarily Heinrich Hertz that observed these. These were observations that sprung from his first discovery. It was discovered that we had electrons emitted from the surface of a metal, emitted from metal surface, when there was radiation of a sufficiently high frequency. When, let's call it electromagnetic radiation rather than light. Radiation of sufficiently high frequency, illuminated, we could say was incident upon, let's say that, was incident upon the metal. Now we call that frequency the threshold frequency. This is the now how do I spell threshold? Threshold frequency. And we've got a symbol for it. We can just call it F0, I suppose, or we could use some other symbol for it. F min, perhaps. Let's use F min. F min. Threshold frequency. Now, this was difficult to explain, because it was before this understood that light was transmitted, and any electromagnetic radiation was transmitted as a wave, and that the amount of energy in that wave was related to the amplitude of the wave. So if I had bright enough light, then I'd be delivering enough energy to get electrons to come out of the metal surface. But here it was discovered that that wasn't the case. So I'm going to make that clear in these notes. It says electrons emitted from metal surface and electromagnetic of sufficiently high frequency incident at the metal. And they call it that, and they can say this is regardless of the amplitude. Regardless of light intensity. Regardless of how bright the light was. It didn't seem to matter. That this could not be explained with wave theory. Could not be explained by wave theory. And I might as well say here, which stated that the power that was delivered was power delivered is proportional to the amplitude squared. We'll get into that in waves later. No matter how high the amplitude, the electromagnetic radiation, didn't matter how much energy we thought we were delivering, electrons did not have enough energy to escape unless that light, that electromagnetic radiation, had a high enough frequency. However, the number of electrons emitted per second, we call them photoelectrons. So we could say the photoelectron emission rate. Photoelectrons are just electrons. They just happen to be emitted during this process. So photoelectron emission rate, that was proportional to the intensity. And therefore proportional to the amplitude squared, as it was understood. If we had brighter radiation, brighter light, higher intensity radiation, then we had photoelectrons emitted at a greater rate, as long as the frequency of the radiation was greater than or equal to that threshold frequency. Then we would see this. The third thing that was noticed was that the photoelectron emission was immediate. There was no delay. And that flies in the face of wave theory as well. Immediate, I can't even spell immediate. That flies in the face of wave theory, because wave theory suggested that as long as the waves were delivering energy for a long enough time, eventually the electrons would get enough energy to escape the metal surface. So we've said a few things here. The electrons are stuck in a metal surface, and to get them out, we have to give them energy. Now we can do experiments. We can take a plate of some metal. Let's just draw a diagram here. Let's just take a plate of some metal, just like this. Usually the metal that's used is zinc. And you can charge this up so it's negatively charged, so it's got an excess of electrons. It makes this a bit easier to see this effect. So let's say zinc, and let's say it's negatively charged. And what we can do is we can place that on something called an electroscope. So an electroscope has a rod that goes down the middle like this. And this is a gold leaf electroscope, which means attached to this is a piece of gold leaf, which usually hangs down straight like that. But it will fly up if there is charge, because gold is a conductor. The charge that the rod down the middle has, which is a metal, that charge will be the same as the charge on the gold. And if they have like charges, they repel. So this repulsion indicates charge. It doesn't say if it's positive or negative, it just indicates charge. And this one here, this point here, has no charge. So what was discovered was that if we have radiation coming in, photons, shouldn't have said that word. Let's edit that word out. If I have radiation coming in of sufficiently high frequency, then it will cause the gold leaf to fall down. It will discharge the metal. What will happen is electrons will come flying off the metal, just like this. Not necessarily in that direction, of course. But if the frequency of the electromagnetic radiation is not greater than or equal to that threshold, which depends on the metal, then it doesn't matter how bright it is, the photoelectrons don't come off the metal surface, and hence the electroscope doesn't show any sort of discharge. It's a very simple sort of electroscope. What we do is we put the whole thing in a big metal box just like this. A big glass box, should I say, not metal, a big glass box, just like that, so that it's isolated and so you don't blow any wind on it. But I'm not going to bother showing that, that box. Okay, so it was discovered that for zinc, UV light was required. Remember, Heinrich Hertz had discovered that ultraviolet radiation meant that we were able to get bigger charges, and it caused bigger charges, I mean bigger sparks, photoelectron emission. And photoelectrons, remember, are just what we call these things. They are just photoelectrons. They're no different to normal electrons, but they're emitted by the photoelectric effect. Now, wave theory doesn't predict this. Wave theory predicts, as long as the light is bright enough or illuminating the metal surface for a great enough time, eventually the electrons will gain enough energy to escape. We don't observe that. So how do we explain these observations? Well, Heinrich Hertz didn't know, but a chap called Albert Einstein, who I think we all recognize the name, Einstein, released four papers in the year 1905, his Annus Mirabilis, and one of them was about this photoelectric effect. What he proposed is using the work of Max Planck. Sometimes his name is pronounced Planck. Max Planck. So what Max Planck had said is that within this particular problem he was looking at black body radiation, he supposed, as a mathematical trick and nothing more, he supposed that the energies that were possible for the light to have were proportional to the frequency of the electromagnetic radiation. And he proposed, so it's nothing to do with amplitude anymore, it's to do with frequency. And he proposed that these energies were quantized. That means they come in discrete packets. Quantized, discrete, and this is ETE at the end, not double ET, discrete packets. And so because of this proportionality, we have the equation E equals HF. And H is named after Max Planck because of this. This is Planck's, spell his name right, Planck's constant, named after Max Planck. H has a value, and it's not a very big value, 6.63-ish times 10 to the negative 34 joules seconds. It's got a very, very, very small value, times 10 to the negative 34. Now, Albert Einstein used this idea, and he said, what if, this isn't a verbatim quote, what if it's not just the black body radiation that behaves in this way? What if all light is quantized? You can see where the idea of quantum theory comes in, the name of it, quantized, a quantity, a set quantity, a packet. What if all light is quantized? And we call those quanta of light, quanta, the plural of quantum, quanta of light, or any part of the electromagnetic spectrum, we call photons. Now, you've met the idea of photons as a virtual particle responsible for the electromagnetic force. Now, well, that came later. First of all came Einstein proposing these photons as a way of explaining what was going on. So our equation E equals HF, we could rearrange it, or we could rewrite it as E equals HC over lambda. That's using the equation C equals F lambda and substituting it. That's a GCSE equation, sometimes incorrectly called the wave equation. And there we go. Now what he said was, look, we had energy coming in and electrons came out. Energy came in from the electromagnetic radiation, electrons were able to come out. But when they came out, they had a speed. In fact, they had a range of speeds up to some sort of maximum. And so if we have a simple energy conservation equation, energy conservation, then we could say that the energy in must equal the energy out. And what is the nature of that energy in? Well, it's what's carried by our photons. And so we can call that HF. And what's the nature of that energy out? Well, some of it is the kinetic energy of the photoelectrons, and it goes up to a maximum. So I'm going to call it EK max. But there's some other place that energy goes, this letter phi, because it turns out that EK max is not equal to HF. This is the photon energy. But over here, that is the maximum photoelectron kinetic energy. And they are not equal. There's an extra bit of energy that came out, which was the same for, as long as you have the same metal, this was always the same. Depends on the metal type. And this is called the work function. Now, why is it called a work function? I'm not going to go into that now. It's a bit complicated. It's because it is actually a function, not a single value, but at A level we take it as a single value for simplicity. So HF is the energy in, this is what's going in, and then coming out is these two. And energy is conserved, which means what goes in is what comes out. So you can think of it as like paying a toll to get through, to get out, to get across the bridge, paying a toll. The photons deliver energy to the electrons, but the electrons have to pay some to get out of the surface of the metal. We call that the work function. So we can define the work function at A level as the minimum energy needed to free an electron from the surface of the metal. Now, it's absolutely crucial that you don't cut corners with that definition. Minimum energy needed to free electron from the surface of the metal. Now, why is that? Well, because photons will actually penetrate into the metal and be absorbed by electrons that are deeper in the metal. And the electrons that are deeper in the metal happen to be moving in the direction towards the surface. They've still got to move through the metal to get outside, which means that there's still going to be work done by those electrons moving through the metal. That's why we get Joule heating, electrical heating, resistive heating. So as the electron moves from inside the metal to outside, moving through the metal, it's colliding with the metal ions, transferring energy to the metal ions, and causing those metal ions to vibrate more, in other words, increasing the temperature of the metal. So that's doing work on the metal, which means there's less energy that comes out, less maximum kinetic energy of the photoelectrons. So this equation we've got here isn't the full story. In fact, if we looked at a graph of the, let's try and draw better axes than these. Come on, we can do better than that. Let's get the straight line tool. If we looked at a graph of the kinetic energy of the electrons versus, let's say, how many electrons that have that particular kinetic energy, then what would it look like? Well, there's going to be some which actually have 0 right at the surface. There's going to go up to some sort of maximum, and then it's going to go down to 0. And there is our EK max. Just like that. And if you have the same energy of photons, but a different metal with a larger work function, then you have smaller EK max. If you have the same metal, but you increase the photon energy, you have a bigger EK max. So we're just using that equation at the top of the screen there to understand what's going on. Now that threshold frequency can now be understood in terms of EK max. F is going to equal F min when EK max is equal to 0. Any less energy than that, and the electrons can't escape. And so we could take this equation and we could replace F with F min and say that's equal to phi, the work function. And we could rearrange that equation at our leisure. Well, okay, that's fine. But what if I don't want to stop the use the threshold frequency? What if I want to measure the work function? What can I do? Well, we can do clever things, like we can stop the electrons getting across a gap. So imagine I've got something that looks a bit like this, and all this is in a vacuum, like this. And I can have light coming in. This is called a vacuum photocell. I can have light coming in like this and delivering energy to the electrons. Better label this a vacuum photocell. That's at the bottom, isn't it? Vacuum photocell. And then what will happen to those electrons? Well, those electrons are going to move from here to that other connector. So I would be able to detect a current because I would have a flow of electrons. So I would be able to detect a current. So let's pop a little ammeter in here. Let's just put that on there. There we go. A little ammeter in here. It's not going to be a very high current, so maybe this should be a micro ammeter. Just like that. We could detect a little current flowing. But if now I connect these terminals to a power supply, and I can do that in a few different ways. But let's connect them to a power supply to make this side more positive, that side more negative. So there's a potential difference between these 2 points. And I connect a voltmeter between those 2 points. Then what's going to happen? Well, as V increases, the electrons that are escaping are more strongly attracted back to that metal. So eventually there will be a particular V where the electrons do not have enough energy to reach the other side of the photocell. And we call that particular V the stopping potential. So we can say when V equals Vs, that's the stopping potential. And you may remember from GCSE that V, voltage, another name for that is potential difference. So when V equals Vs, the current becomes 0. So we can measure the current and then increase V bit by bit by bit until it's Vs. Now, how much work has been done by the electrons moving across this photocell? Work done on electrons or by electrons moving across photocell is going to be equal to, let's call it a W for work, is going to be equal to the charge of the electron multiplied by the potential difference it moves across. So when W equals EK max, in other words, when the energy that's going to be transferred and the electrons moving across that gap is equal to the maximum energy the electrons can possibly have, then the current will fall to 0. then I becomes 0. And so our equation becomes HF is equal to phi plus EVS. Just like that. And now we can measure VS for different F's, and from that determine what phi, yeah, I got it in the end, what phi is equal to. So yes, the electrons manage to escape, but they are not necessarily going to get out of the to the other side of the photocell. Right, these notes are a little bit of a muddle, aren't they? So let's move the photocell diagram down and move the title up. I did this last time with the notes, and I think it's worth doing when they're, oops, I made the title bigger. At the end of the world. Let's move the vacuum photocell down. Let's move the title up. We don't need the brackets. Vacuum photocell. Let's delete this. Where's the delete button? There it is. Let's underline the title vacuum photocell. There we go. And then we've got our notes right there. In fact, let's just move some of this around again. Let's put this up here. What does that look like? Energy conservation, blah, 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 blah. Yeah. That really wants to be attached to that, doesn't it? I'll tell you what I'll do, something I don't very much like doing. I'm going to draw sort of a wiggly line over here so we can see that all this is to do with the vacuum photocell. Don't really like doing that, but that's going to be a little bit easier to make sense of the notes. Right, there we go. And that is your introduction to quantum physics, to quantum phenomena, the photoelectric effect.